Hello and welcome to the Open Source Silicon Stream number 13. And today I've got a very special guest who's going to join us shortly, Leo Moser, to talk about his experience with the open source tools and flow and his latest chip. So we'll be getting onto that later, but let's start off with some news. So first up, I wanted to mention that we've got an initial agreement in place with chipfoundry.io, which is the company set up by Jeff and MKK, who previously were at eFabless, and they're offering Sky 130, very similar to before, but slightly different. So definitely check them out, chipfoundry.io. And the first shuttle should be going live with them sometime in September. And you can read the announcement that we made about that on the Tiny Tape Out LinkedIn channel. If you're hearing this, maybe you can just send me a comment, drop where you're listening from, tell me if the audio is okay, that kind of stuff. And then let's see, what else have I got? So very brief update on SpaceX. So if you want to know what's been going on with the plan to get Tiny Tape Out 6 into low Earth orbit, then check out last week's stream, and also did an interview with Tibor and Pat about the satellite itself. Pat has finished the hardware, and Tibor is imminently going to be receiving that for integration into the satellite. And then we've got until May the 29th. Let me just double check that. On the SpaceX, May 28th. So if you want to get your Tiny Tape Out 6 design tested in space, or even if you don't have a Tiny Tape Out 6 design, but you want to test somebody else's design, check out the SpaceX channel on the Tiny Tape Out Discord. Andy says my intro was cut off, but now I'm live. Thanks, Andy. Good to see you. Julian says, tuning in from Philadelphia. Good to see you, Julian. And Sylvan saying, audio is good there. So thanks for the feedback, everybody. Let me just put the Discord link there. So if you want to get involved in SpaceX, join the Tiny Tape Out Discord, check out the SpaceX channel. We'll be giving you like weekly updates, but basically you need to make a pull request on a repository by May the 28th. I think we've got 3 or 4 already integrated there, including I did one that is going to be measuring the frequency of Uri's ring oscillator. So the idea with that is the ring oscillator should slow down and speed up as it moves, as the satellite orbits the planet. So I'm looking forward to seeing that happening, and hopefully if it all does go to plan, I plan to get back on my STR games. I used to capture some of those GOES satellite images with a helical antenna and a RTL STR. So once our satellite is going overhead, I'll be outside with my positional antenna trying to capture some signals. That'll be fun. Right, and I think I've got one more bit of news. Oh yes, so just a little bit of housekeeping news. I'm going to be traveling this weekend, so I'll be returning on Monday. So I don't think there's going to be a stream on Monday. So I'll skip a week. But stay tuned, and if that does change, then I'll let you know via the usual channels. Okay, so without further ado, I want to welcome Leo onto the stage. How's it going, Leo?
It's going fine. Yeah, thanks, Matt.
Yeah, cool. So I can't actually remember where we met, but you kind of came up into my field of view of being one of the people that was kind of like actively making designs, contributing to software. You even worked with eFabless for a while, and now you just posted about a really large chip design called Greyhound. So I want to get into all of that in this interview with you. And for people watching, feel free to drop comments as we go, or questions, and we can answer them. So maybe, Leo, you can just tell us, like, how did you get started with open source silicon?
Yeah, so there was a time where I didn't even know what a PDK actually is, like for many of us. And actually, when did all of this really start? Of course, in 2020, when Sky 130, the first like proper manufacturer manufacturable open source PDK was released, and yeah, at that time I just yeah, it was overwhelming, all of that information, and you could just access it. And basically, I tried to get all of this in, but I didn't really do anything with it yet. I didn't do any designs. I watched other people do their designs and submit to their Open MPW shuttles that were yeah, sponsored by Google at the time, and only really yeah, at around MPW7 and MPW8, I submitted my first designs.
Okay.
And yeah,
Late to the
so
party.
yeah, you could say. But I've been kind of yeah, viewing all of that, and then I actually started with my bachelor thesis. Submitted the design on MPW7. It was called a waveform generator, a full digital design, and then yeah, from there on, it just went on. And after the Open MPW shuttles were discontinued, I also started to submit to Tiny Tapeout, of course. And I also did this like tiny VGA PCB that you will probably know, so that we all have a common pinout for yeah, for VGA monitors, and we can easily there it is. We can easily just try out different designs. And yeah, it also shows I love to do like visual designs. We also I submitted a tiny shader to one of the later tiny tapeouts, and basically it's a design where you can upload your own small custom shader, and then it will display it on the VGA monitor. So yeah, this was all nice. And then yeah, I basically got to the point where I was doing my master thesis, and I had to think about, yeah, what do I actually want to do? And of course, I would like to do like another open source chip design. Yeah, and yeah, just for information, I'm studying at Graz University of Technology, and basically, I was always quite impressed, yeah, by FPGAs. That's basically how I got into all of this, yeah, into the whole space, learning Verilog and so on. I started with the Icebreaker FPGA.
Yeah, I was going to say, what's your first FPGA board?
There it is.
Classic. Nice icebreaker.
Yeah, and the special thing about this one is it has an IS-40 on it, and this one was reverse engineered, so you could really use it with open source tools, with Yosys and NextPNR. And after that, I started with the ULX3S.
Yes.
So continued development there. Tang Nano 9K, and the latest addition to my FPGA DevBot collection is the GateMate A1 from Olimex.
Okay.
And yeah, what do they all have in common? They can be programmed with Yosys and NextPNR, so it's really hands-on. You can just yeah, super easy to design, and you don't need all of that proprietary software. And
Yeah.
that's what I also love about, yeah, free and open source silicon.
That was also my road into the whole FPGA world. And
Yeah.
I think if I hadn't have had FPGA experience, I would have thought that the Google sponsored lottery was great, but I don't think I probably would have actually submitted anything. It was that I had already had a little bit of the experience with FPGAs that kind of gave me the confidence to try it out.
Yeah, I even watched some of your like tutorials on Yosys HQ, I think it was.
Yeah.
Yeah, so thank you for that. Really.
Yeah, no, big shout out to Claire and the Yosys HQ team for like enabling all of that work. And I know we've got Sylvan here in the watching, and Sylvan's contributed a lot to the open source FPGA movement, including doing some crazy things like running Doom on the ICE-40.
Yeah, I saw that one.
Yeah.
Wow. Yeah, so I got to the point of my master thesis, and I thought, yeah, why not combine things? I would like to create not only a RISC-V SoC like I did before on the OpenMPW shuttles, but I would also like to create my very own FPGA, embedded FPGA that is basically connected to the RISC-V core. And well, where do I start? But luckily, there are already some frameworks that you can use, and one of those is called Fabulous. And luckily, it basically it uses Yosis and NextPNR. There's also another one, OpenFPGA, I think it is called, which is using the VPR project. Yeah, and this is like, yeah, it's different tooling. But I was quite happy with Fabulous, and that's what I use to generate the embedded FPGA of Greyhound. Yeah, and basically I had this idea, and I found this great, the Embedded Architectures and Systems group at my university, EAS, and I just told them, yeah, I would like to do that, and they were absolutely happy with that. So my supervisors, Tobias Scheipel and Meinhard Kissig, yeah, they really supported me with that idea, and I'm very happy that it's worked out everything so well.
You're at the same uni as Meinhard?
Sorry?
You're at the same university as Meinhard?
Yeah, really.
Yeah,
Phasey RISC-V. Shout out to Phasey RISC-V.
Yeah, Phasey. Yeah.
You can have a look at it later because it also runs on the FPGA of Greyhound. So there's enough space, but we will see.
Great.
Yeah, so perhaps maybe I should start sharing some.
Yeah, and I also just mentioned that I interviewed the Kirk and the Fabulous team probably 2 or 3 years ago when they were doing a dual RISC-V core with an eFPGA, and the eFPGA was also generated by Fabulous. So I can I'll link that in later when I edit this for YouTube.
Yeah, so Fabulous, they themselves also did quite a lot of tapeouts also on the OpenMPW shuttles, and they did really interesting work on there. So yeah, you or everyone listening should definitely check this out. Yeah.
Yeah. So what did you want to show us then on your design first?
Yeah, I would say let's start with the repository, because I've kind of put all of the documentation in there, so we can just go through it. And yeah, so is this already visible?
Yep.
Perfect. So here we see Greyhound, a RISC-V SoC with tightly coupled embedded FPGA on IHB SG13G2. And the thing is, actually, it wasn't my initial goal to tape out on IHB, but when I worked at eFabulous, during my master's, I would have had the opportunity to also put Greyhound on one of the ChipIgnite shuttles. So I actually started Greyhound targeting Sky 130, but as we all know, eFabulous, unfortunately, they shut down recently. So I had to basically, switch to IHB on the fly, and it all went well. It worked, and that is the chip that you can see here.
It kind of looks like the Caravel chip, doesn't it? With the bit at the bottom, and the patching is pretty similar.
Yeah, not the first time that I've heard that. The reason, why the patching looks like that is because I'm using the same patching as you guys are using it for tiny tapeout.
It certainly will make it cheaper for getting things packaged.
Definitely, that was the idea behind it. And also big thanks to Sylvain for like matching the pad frame, because he also did some changes to the tiny tapeout pad frame so that it really works between these two versions we have there. So and you're right, actually, at the bottom we have the SoC. So this is where the RISC-V core with some SRAM is, and then at the top, the large area here is the embedded FPGA, and also on the right some SRAM blocks. So yeah, from the feature overview that we can see here, I've used the CV32E40X RISC-V core. Yeah, why did I use that one? Maybe just
You love the name.
yeah. Well, actually, I've used it before, so
Yeah.
I was already aware of it. And there's one special thing. It has a custom instruction interface. So you can easily just plug in a custom instruction module, and then it will just execute custom instructions from there. But it's quite sophisticated. So you can also do like CSRs and also access the memory. So you can do a lot of stuff with it. And I thought I might also need it. Didn't need that many features after all, but yeah, that's why I chose this core. And the thing is, it uses quite a lot of system Verilog. The core is from the Open Hardware Group, and yeah, so I had to convert it into a format that is easily readable by users. And I've used the system Verilog to Verilog converter. So this one worked
SV
really
to V.
mhm,
Yeah.
SV2V. So
Is
this
this
one
from
worked fine for me.
ETH Zurich?
Actually, no. This one is a different project, but
Okay.
ETH Zurich, I think they're using Slang, and that's also something
Oh,
that I want to look into in the future.
yeah.
But here I've used SV2V. Yeah, and then of course we need some IP cores. Yeah, of course the built-in SRAM from the PDK, so 8 kilobyte of SRAM for the SoC.
Yeah, that's actually interesting. Let me ask you about that because I didn't
Sure.
realize that the IHP PDK included an SRAM.
Yeah, really. There is some SRAM in there. Unfortunately, quite strange sizes. Like you have a word size of I think 16-bit, and then I think also 48 and 64-bit. But there's no 32-bit one that I actually wanted. So
Yeah.
basically, for the FPGA, I just combine two SRAMs in parallel to get like the 32-bit data width.
Okay.
Mhm.
They look
So
nice and
this,
small though. They look a lot more efficient than Open RAM.
yeah, that's for sure. Yeah.
Do you know where they
Mm.
came from?
I would assume, yeah, they are coming maybe from their proprietary PDK. Maybe they have some
Hmm.
kind of so the SRAM compiler that they've come from is definitely not open source. So it's like just these are the blocks and you can use them and that's it basically.
Hmm.
But we know
I
there
saw Van
is
saying that they come from a commercial generator. That's interesting to
Mhm.
know. Yeah.
Yeah,
I
but
thought that that was very difficult to do because they would be like all encumbered with kind of IP stuff.
yeah, but I guess HP they managed to do that.
Yeah, that's a good job here. They
Yeah.
hopefully they're paying their lawyers nicely.
Also noteworthy, there is currently an open SRAM compiler in development by Staff Verhagen,
Yeah.
and like he's creating, which can also do like a red hat SRAM for space, which would be interesting for Tiny Tapout now. So will definitely be interesting to try this SRAM generator out because as far as I know, it should also be support dual ported SRAMs, which would be super useful for FPGAs, of course, because yeah, for block RAMs you actually want dual ported, and here I only have like the single ported SRAM. So that's yeah, that's the thing. So yeah, SRAM. Then we have some quad SPI IP, one flash controller. This is to get the bit stream.
Mhm.
Not the bitstream. I mean, also the bitstream, but this is to get the program code for the and the data for the SoC, of course, for the RISC-V core. And then there's also a PS1 controller to basically, yeah, 8 kilobyte of SRAM might not be enough, so you can
Mm.
add some external one.
Did
And
you write all this IP yourself, or were you able to reuse it from other sources?
yeah, good question. So, which things did I actually develop? Mostly the configuration logic around the FPGA.
Mm.
So where did this IP come from? And that's actually, so we can have a look at the IP folder here. That IP actually comes from eFabless.
Okay.
So we have the PS RAM, quad SPI, PS RAM, then the flash controller, and also the UART. Of course, all of the repositories are now forked, just to be sure.
Yeah.
Yeah, but actually at eFabless, we had this really nice new chip in development called Frigate, and it basically should have replaced Caravelle, because Caravelle, it is nice. It has a RISC-V core, but actually there was a lot of improvement that you could do, and Frigate basically would have been that. And there is actually, I think, a Frigate OS repository at eFabless. So this one was still released, but unfortunately, all of the configuration files for OpenLane and so on are not. It would have used the new Panamax pad frame with 128 pins. So yeah, I would have loved to see that become a reality. But who knows what will happen in the future? The source code is still here, and I know that Tim Edwards would really love to see that become reality.
Sylvain is asking if the PS RAM controller is also cacheable.
Yeah, very important point. Yes, it has a built-in. The PS RAM one. No, unfortunately not. But the quad SPI flash controller, it has a cache, because otherwise, it would just slow down the whole system. And where do I see it? I think there's the standard setup, but I had to turn this down a bit to get everything to fit. But I have basically 8 lines of 32 bytes. And this is really important. Like, it really speeds up, like all of the, for example, in the CRT0, all of the initialization and so on. It can just happen in the loop, and there's no fetching of instructions from the outside. So really, really important. And that's also something that Caravelle would be something that would have need to be improved with Caravelle, because all of the cache setup and so on was not quite perfect there. Yeah. And there are 2 additional peripherals, the fabric config peripheral and then the fabric peripheral. This is to configure the fabric, the FPGA, and this is then to access the FPGA as a peripheral. So you can then implement a peripheral inside of there, and then the CPU can access it. And maybe you want to implement another UART or something else entirely. That's possible. Yeah, so any questions there so far?
I've been asking them as they've been coming up, so we're good to continue.
Perfect. Yeah, because I don't see them, so you just need to interrupt me.
Okay, yeah. I'm like sharing them on the screen and reading them out when they come up.
Perfect.
Yeah.
And then maybe even more so interesting, we have the Fabulous eFPGA. And let's go to here. So this is the Fabulous embedded FPGA framework. And yeah, it is built up into tiles. So you first define your tiles, implement your tiles, and these are then stitched together into a larger fabric. And for that, I've actually written a custom OpenLane plugin. We can also have a look at that later. But yeah, so what are the primitives that are, or basic elements that are in this FPGA? So we have 32 IOs. We have, unfortunately, not quite 1K of LUT4, so 784 LUT4s plus flip-flop. And also it implements a fast carry chain. We can have a look at the primitives in detail a bit later. And there's also something very special about this FPGA, maybe compared to an ICE40, because it actually resembles the architecture of an ICE40, with the exception of these muxes inside of the configurable logic block. So you have like 8 LUT4s in one configurable logic block, and the outputs of those that feed into one of these muxes, and they can be configured to 1 mux 8, 2 mux 4, or 4 mux 2. Basically, that's a secret superpower, because right now that isn't used at all automatically by the Yosys and next PNR flow. So you need to instantiate that manually. But hopefully in the future that will also just happen automatically. we have
We've got a
7
couple of
SRAMs.
questions
Yeah.
coming in about the FPGA. So Rohan's asking, how much block RAM can any FPGA accommodate, given that single port block RAMs are more area efficient than dual port block RAMs?
So how much can we accommodate?
You don't see the thing on the screen that I'm sharing.
Yeah, no, I don't see that.
That's a shame. Yeah,
But I mean,
I'm not totally sure I understand the question, to be honest.
yeah, I
Uh,
mean we have these blocks here. So on the right, these yellow blocks here. This is one SRAM, and that's just the size of it. So
mm,
um, basically, yeah, they are single ported. If they were dual ported, they would approximately be double the size. So that already helps. But it would be nice to have dual ported. So that would be worth it. But I don't have I didn't have the choice there.
mm,
And basically, I could have used less, maybe less LUTs, less lookup tables, remove the arrows maybe from the left side and added another row of block RAMs there,
mm.
added all of the arrows on the top. So I would have had the opportunity to add those things. But I thought it would be, for this type of fabric, for this size, these 7 SRAM blocks are absolutely okay.
And Sam Ellicott is saying, how does the RISC-V core communicate with the FPGA fabric? Is that what the fabric peripheral was?
Yeah, yeah, exactly. So I'll come to that later because there's some more stuff down there. So
Okay.
maybe just let's go through the list here.
Stop interrupting you.
Yeah, no problem. So we have these SRAMs, and actually they are connected to super tires. So if you have a look here, these tires at the right, they are actually 2 single tires high,
Mm.
so that they have like a better connection to the FPGA fabric. And there are also super tires in the middle of the fabric. So these ones here, these are the DSPs.
Oh, yeah.
So we have
Okay.
7 DSPs.
Cool. I didn't know that Fabulous supported DSPs.
Yeah, so our DSPs, yeah, multiply, accumulate. Not even sure what's where you draw the line. So yeah, you can actually do that yourself, and you can also add primitives yourself. So maybe just there's also this register file primitive, which is really useful because it's a small memory, but it has like 1 write and 2 read ports. So super great for implementing, for example, a RISC-V register file. So you save a lot of area there. And one maybe drawback of the whole thing, we have 1 global clock network. I mean, with this size, maybe it's not that much of a problem, but you only have 1 clock available, and that's it. And now these tiles here, they were designed by me. So the warm boot tile, basically, it provides the functionality that the FPGA fabric can reconfigure itself. And you can choose a slot, one of 16 slots, and then it just triggers the reconfiguration and it loads a new bit stream using the fabric configuration. There's the CPU RRQ tile, so you can also send up to 4 interrupt requests to the CPU. And then there are these CPU interface tiles. They're basically the interface to the SoC. Basically, each one of them provides 16 IOs, so 16 in and 16 outs, and I just wire them up the way I need to or want to, and with that I can do the interface. Yeah. Here we can also see the frequency of the SoC of the result of the STA, static timing analysis. There's actually quite a difference between the fast and the slow corner.
Yeah.
Yeah. Initially, I also got a lot of hold violations while implementing the chip, but we'll get to that also. Here's also another overview of just the fabric and all of the tiles. So down here we have a memory map of all of the peripherals. And yeah, then there's the fabric configuration peripheral. And now we have many different ways to configure the FPGA fabric. Maybe I should start here. So the initial goal really was that you can use the FPGA and the SoC just standalone on their own, but then also they should be able to communicate with each other. So the FPGA fabric can also just load a bit stream on its own with this SPI controller, or also with the SPI peripheral. It can receive a bit stream from like an external microcontroller. And there's one pin that you either pull up or down, which chooses between these two modes. And then you have here your SPI lines, and then either it will start fetching from the SPI flash or it will wait for bitstream data. So that's one thing. This goes to the fabric config, and the fabric config then configures the embedded FPGA. But you can also write a bitstream from the SoC. So there's a way to just write a bitstream to a specific memory location, and that's it. It goes into the FPGA. But the SoC can also just trigger a reconfiguration, basically. It can trigger the SPI controller, so it doesn't have to do anything on its own. It can do other things, and meanwhile, the FPGA fabric reconfigures it. And then there's the way for the FPGA fabric to also reconfigure itself with the SPI controller via the warm boot tile. So these are all of the modes. I've added some description here and also some estimates how long it will take to reconfigure the FPGA in real time at certain frequencies. Yeah, so this is the fabric config peripheral. You have your registers. The first one, this is now the special register. Here you can decide whether your FPGA fabric acts as a custom instruction or as a peripheral. So you basically need to set this here. Thinking of it afterwards, it would have actually made much more sense for the user design in the FPGA to set this bit, because it will know if it is either a custom instruction interface or a peripheral. But in this case, yeah, I did it the other way around. Then there's the config busy bit, just to see if a configuration is currently underway. Here you can just write your bit stream. And with this, it's also possible to do a partial reconfiguration of the FPGA. So you can just send in just one frame or more and just reconfigure, for example, a column of tiles. Or you can trigger the reconfiguration, and the SoC can just lean back and do something else and wait for it to finish. So these are all of the ways to configure the FPGA fabric. Yeah, so.
And how about the, I think, like getting to maybe what Sam was getting at. You've configured your FPGA. Can the RISC-V send data like over a parallel interface, or like the FPGA can be kind of reading from a series of A to Ds and then providing like the crunch numbers after some filtration or something like that to the RISC-V?
Yeah, good that you were asking. Almost forgot about it. So you can do a custom instruction extension, or you can implement a peripheral. And if you choose if you choose a custom instruction extension, then basically you have to write the firmware on the SoC, and you just issue that custom instruction. And yeah, initially I thought I would just make use of the whole XIF interface of the CV32E40X, but instead now it's just very simple. You supply the two operands and you get your result, and you also specify the delay slots. So after 13 cycles, the result will be basically read out of that custom instruction here. So this is the first way to communicate with the FPGA fabric, and the other is to write a custom peripheral. The fabric peripheral. So if it's set to 1, then it just is implemented as a peripheral at address 0x5.
Okay, so then it's just like mapped into the memory of the RISC-V core.
Yeah, and which bus interface do we use? So the CV32E40X uses the OBI, the Open Bus Interface. And this one, I think the standard is at the hosted by the Open Hardware Group, and also the ETH Zurich and the like the Pipe platform. They have a lot of IP for that. So there's like a multiplexer, demultiplexer that I use in the SoC. They also have a crossbar, but I didn't have enough area for that, so it's really great. And at that point, I also would like to mention the Croc platform. So this is an educational SoC by the ETH Zurich, and they also tapped it out on IHP, called MLEM, the chip, from the sound Yoshi makes.
Okay.
And I could really use this as a template how to wire up the core, because yeah, you need to know how to use those IP cores, so that really help. Yeah.
So hopefully that answers Sam Ellicott's question. I've got a question on this for you, which is what was it like using all of these open source IP cores? Was it like easy to get started? Were they well enough documented? I think this is like an ongoing theme is, when you pay for some proprietary IP to build a chip with, it's going to come with everything that you need. And it's been fairly like difficult to have a standard, or that you can find some open source IP, but the documentation is missing, or it's never been silicon proven, or all these considerations. What's been your experience?
Well, I didn't have any issues at all. So for these free IPs, of course, I was at the source. I was at eFPGA, so I could have just asked them if something wasn't clear, or if there were some bugs. But if that weren't the case, I would have just created issues on in the repository and asked for help that way. But there were no issues at all. I had to do a bus bridge between OBI and AHB Lite, so that was the only issue. But otherwise, it worked, and also with the IPs from the Pipe platform. There were no issues. There were other issues that were made by me, but I managed to fix those. During the verification. I mean, verification is also another important point, because I actually ran like a chip top level verification, really probed the pads and made sure that the output enablers and everything is correct. And I tried all of these configuration, all of these ways, simulated them in using the gate level netlist of the SoC. The Fabric, unfortunately, only works with the RTL netlist for now, or code for now, because the standard cell models, they are too pessimistic, and suddenly the X values propagate everywhere. But we know that the fabulous FPGAs, they themselves, they work, because they've
been taped out multiple times, haven't they?
So that shouldn't be the issue at all. So, but maybe we can also have a look at the chip here and at the physical implementation, because this was actually the hardest. So I switched from Sky130 to IHB, and I basically had to redo all of the tires and the FPGA. So this block here is the FPGA, and this one is hardened using my OpenLane Fabulous plugin. It will stitch, or first it will create the tires and then stitch all of them together. It will make sure that all of the pins and so on are correct. And then you just have this big block here. So right now you can see much. But then at the bottom, we have like the whole SoC. And initially...
So let me just go back to the FPGA stuff. So when you say OpenLane, I guess you're meaning OpenLane 2?
OpenLane 2, of course, yeah. And soon it will be called a library lane, by the way.
That's it, it's been transferred to the FOSSI Foundation.
But this is still a work in progress.
Yes. And one of the big things about OpenLane 2 is the kind of the plugin support system. So you wrote your own plugin that can basically do all of the stuff that's required behind the scenes to get the fabulous FPGA working, or?
Correct. So this is the OpenLane plugin Fabulous, and I think I even have some images here. So for just single tiles, it will place the pins and also place the PDN straps all the way to the boundary, because We really we place the tires directly next to each other, no space in between, so everything has to directly match. And yeah, there are some things to consider, that all of the pins are on grid, and also that the size basically is a multiple of the routing grid. And then
So
you
there's no
just
routing done afterwards. They just like clip
really,
together and
yeah.
everything lines up.
Mhm.
Yeah,
It's actually super fast to do the fabric
nice.
itself then. And then we also have the super tires, and here you need to consider that these pins here need to be centered at this point, and these pins center at this point. So basically I had to hack the open lane pin placement script a bit, had to adjust it for Fabulous, and yeah, that works fine. And
Nice.
for the PDN, because I only have like the vertical power straps here, because I want to add the horizontal ones at the top level. I don't want a PDN ring,
Mm.
but they are not they're not pins of these markers. They're not top level pins. So
Mm.
basically, in the plugin, I place PDN straps at the same locations, just so that they are registered as top level pins, and then
Hmm.
everything works out. And yeah, that's what we can see here. So here we have
Okay.
these are the PDN straps that go
Okay.
down
And
here.
then they're dropped down from the vertical lines, the horizontal lines. Yeah.
And then they connect. And HB, we have top metal 1 and 2 for the PDN, and even top metal or metal 5, I think, is even used because of the setup. I mean, the HB PDK is still pretty much in development, and yeah,
It's 7 metal layers, right, on the IHP PDK?
mm-hmm, yeah, should be 7. Yeah, we have it here on the left.
Oh, yeah. Yeah.
Yeah,
Oh, top metal
and
1, metal 2. Okay, yeah.
exactly.
Hmm.
And well, it was around 1 week before the final submission, and I thought, yeah, just finish everything, put everything together, it will be fine. But then I came to the physical implementation, place and route of the SoC, and I just got hold violations everywhere. And as we know, hold violations are very, very bad, because you can't basically fix them afterwards by just running the chip slower. You would maybe undervolt it, but it's not really feasible. So why did this happen? Because at first everything was okay, and only after SPEF extraction I got this totally skewed clock tree, and that's why I got hold violations. So somehow the RC estimates didn't really match the SPEF extraction. And I mean, one thing that also led to this is because initially I've also used the space left to the fabric. So I actually placed standard cells everywhere here, because we have like for each row, we have 32 data inputs, and we have our flip-flops here. So it makes sense if you can place them directly there. But this makes a long L shape, and
Mm.
basically the clock tree is also all stretched out, and this made it much more worse, this mismatch between RC and SPEF. So one solution was to basically only allow the standard cells down here in the core area. And the other thing was to basically hack a bit around in an open lane in the PDK setup, because the way how the RC estimates were set, yeah, if you don't set it manually, then it would use the one from the TechLev, and that worked much better. And so I could fix all of the hold violations.
And how were you able to do that? By like changing the way you were placing things, or using a different type of clocking methodology? How were you able to solve that?
Where the clocking methodology is just a simple clock tree, really at this top level.
Mm.
And yeah, by limiting the core area to this area down here, this helped a lot. And then also the configuration in open lane, and
Mm.
that basically fixed it. But yeah, you mentioned clocking methodology. The FPGA itself actually doesn't have a clock tree. It uses a clock ladder. So the clock is basically input at the bottom, and it goes from row to row, and
Mm.
basically is delayed by a bit. And this also needs to be considered in the place and route of of your user design. So next PNR needs to consider that, and it already has support for actually printing hold violations, so it can detect them, but it doesn't fix them yet. But I'm also not sure if this will be like a big problem, because the previous Fabulous fabrics also, they worked quite well. I think there
Mhm.
was an issue where the SRAMs, they got their clock from the clock tree at the top, but I actually supplied the clock from the actual row. So this makes sure that the signals are in phase with the clock, and this should
I never heard of a
make
clock
sure that
ladder
they work.
before.
Yeah, that was also the first time for me actually.
Yeah.
But it's quite a simple concept. And actually, if your data goes with the clock, with the clock wave, basically this helps you because you have more time to do any calculations, your more setup slack. But also, yeah, it reduces the hold slack, and this can actually lead then to hold violations, even on a 140 nanometer process.
Okay.
Yeah. So
So
this
would you say
really to be
that dealing
considered.
with the hold violations was the trickiest part of the project?
Hold violations in the SoC. Yeah, definitely. I put a lot of time into fixing that, but in the end, it worked all out.
Yeah. Well, fingers crossed for the actual silicon, eh?
Yeah, thanks.
Looks like your SoC is on fire there with all the text on the right hand side.
Yeah, I mean, horrible. All of
The
these
smoke is
layers.
coming out.
It's just yeah, it's just too much. But what I also wanted to show you is like is it? That's the wrong one. Here we have the GDS with logo, because I've added the logo only afterwards. I added a blockage during place and route. If anyone else knows a better method to do that, please just let me know. So load layer properties.
Where did the name and the logo come from?
Greyhound, basically, yeah, I think they are neat dogs. So that basically was the reason for the name. And there's also this meme.
Let me do it for you.
Yeah, maybe you've seen it already. There's like
I'm not familiar with this meme. No.
there's someone trying to get the last Pringles out of a Pringles can, and then there's
Okay.
like the dog, and yeah, it says, "Let me do it for you," and then with the long snout, it's just
Okay.
yeah, really funny. And yeah, so that's the logo. Also, first time that I'm using non-45-degree angles on the layers here,
Yeah.
but I think it turned out quite well.
Yeah.
Yeah.
And this has been submitted onto the which shuttle? Actually was the early one. Was it the April IHP
Mhm.
shuttle?
Exactly, early April. This was. Mhm.
Yeah.
Yeah.
You
So
didn't find any last minute bugs and resubmit it onto the May one.
thankfully not. Yeah, not yet, at least. But I also, yeah, I mean, I did the DRC check, all clean, of course. I also did LVS, abstract LVS, because the extraction of the I/O pads with Magic doesn't work yet. So yeah, PDK is still in development, but I've used abstract LVS, so with the left def fuse, and this also should pretty much make sure that the design is correct. So I'm quite optimistic that it will work.
We've got a question from Russell who wants to know how long is it going to take to come back from IHP?
No idea, but I would guess around 6 months.
And Sylvan is saying end of November 2025.
Okay, there we have it.
Matches up. Yeah. Yeah. So do you already have like a bring up plan?
Yeah, I mean, I have all of these scripts, and I've also all of these tests that I basically ran.
So you should be able to just
they're
run all the simulation tests.
Yeah, exactly. I mean,
on the hardware itself.
That's the best case scenario. It should, just run, and otherwise I will need to debug. But yeah, that works. Also, I've just earlier I've got some questions from Sylvain on Mastodon, so maybe I'll just answer them.
Cool.
Is there a roadmap schedule for timing data? So yeah, that's also another thing. Right now, there's no timing data exported from Fabulous, which is of course not that great because you don't know how fast your design will actually run. But actually, this is in development by Fabulous. I could attend the latest development call. I was invited, and yeah, I can't talk about everything that was discussed there. There are a lot of interesting things are happening right now. But yes, timing data is on the roadmap and soon.
Mm-hmm.
And regarding the I/O blocks, double data rate gearboxes, no, those are really, really simple I/Os that the Fabric uses just input, output, enable. But you can customize them. You can make your own primitives and tires and add them to the Fabric. And then full wishbone bus, no, it uses the open bus interface. Yeah.
Mm.
And how is timing handled on that? Yeah. Actually, I didn't do anything specific there. It's just I connected it as it is. So with the custom instruction interface, you can select like the delay slots after how many cycles you will read the result. So that should help. And also with the yeah, I guess you will just have to run everything slower if necessary. But yeah, that should be okay. I think there shouldn't happen hold violations because the clock is delayed in relation to the Fabric from the clock tree to there. So basically, I think this should help avoiding hold violations. And there's also quite a lot of logic in between. So yeah, but there's just a lot of testing that I will have to do then when it's ready.
Russell is asking, is there any built-in self-test?
Well,
That's you, is
no.
it? You're the built-in self-test.
So there's no scan chain insertion for the SoC, but that would be great. Would be nice to see. And yeah, the FPGA itself, I'm not sure if commercial SRAMs have a test mode or something. I think that would just need a lot of area. I think you would just test it by uploading bit streams and yeah, making sure that that it works. And the SRAMs themselves, they have another port for a built-in self-test, but you can only choose yeah, one of the ports running at the time. So it's basically a multiplexer, and you could test there.
Great. So, what's next for you after this? Are you going to
Yeah.
continue to build chips? So you're going to stay in academia? Are you looking for a job in the commercial field?
Well, I'm going to see. Also, I will definitely continue making fuzzy chips because yeah, it's just so much fun. Right now, yeah, I will just continue my master thesis. I still have to write it, unfortunately. It's like taking the most effort, but afterwards I will see. So maybe academia, maybe working somewhere,
Yeah.
but definitely in connection with open source silicon.
Yeah. And for people who doing this, thinking that open source silicon is an interesting field that they would like to get into, what would you recommend as like a starting pathway?
Yeah, tiny tapered, of course.
Of course.
Yeah, I mean, really, I've also recommended it like to my university, also where I was before for my bachelor's, and they're interested in starting a course there, and also for analog IC design, where I'm currently also a teaching assistant at TU Graz. There we also plan to submit to Sky 130, but right now, yeah, without analog support, that won't work yet. So we will submit to or try to submit to IHB. But once there is also analog support back into place for tiny tapered, yeah, that will be very interesting.
And how you also got some experience with minimal fab?
Yeah, I did actually.
Didn't you win a prize?
Yeah, yeah, twice actually. Yeah, so there's the ICPS PDK, which is also an open source PDK for the minimal fab system. And yeah, you can do your designs with that. I guess mostly analog because yeah, it's quite large. So transistors are like 6 micrometers effective gate length. So mostly analog stuff you can do with that.
And the wafers are like 10 millimeters or something, aren't they? They're tiny.
Yeah, they're super small. I think we even did an interview once. So there I actually showed the wafer.
Yes, I think
it's really
right. Yeah.
small like that. Maybe I just want to show how to compile an FPGA.
Oh yeah, you said you're going to do a demo. Yeah, we've got 5 minutes left.
Yeah. So
in the meantime, if there's any more questions for Leo, get them in quickly.
Exactly. So, for example, here I have all of the examples that I've also used for the verification, like the custom instruction interface and so on. And here's just a counter. So I just run make and okay, I need to source the tools. Now it's running. So Yose's next PNR is already done and the bitstream is generated. So okay,
that was quick.
It's fast, yeah, for such a small design. So
that was actually
runs
the thing that convinced me to start using the open source FPGA tools when I first was learning, because I had an iteration loop that was like 10 times faster at least.
Yeah, that is really important. So here we have the output of Yose's, and then here we can see how much area is used on the FOC on the FPGA fabric. These I/O one bidirectional frame config bus, these are just the I/Os. That's the default name from Fabulous, and yeah, maybe they should change it. But here we use 42 of the I/Os, 6% of the logic cells, and yeah, basically that's it. It runs the place and route, and in the end, it generates the bitstream. So that's it. Maybe more interesting, I have also the serve bit serial RISC-V core and the FASI RISC-V. So if I run, yeah, from Meinhard. Yeah, so if I run here make, this takes a bit longer. And it uses up 69% of the resources here. So this is like the smallest configuration, but it fits. So this is really great.
Inside. Yeah, that's
great. Also, it uses this register file tiles for the RISC-V register file automatically, and also one of these SRAM blocks for the SoC. And
any of the DSPs?
No, not yet. I think they are not automatically inferred. That would need to be added.
I've got one last question from Sam saying, what process do you use for top-level verification? I think we covered that a little bit, didn't we?
Yeah, so CocoaDB, I'm using CocoaDB, which is really great. I can write my test benches in Python. And then I use Icarus Verilog because it has a, four-state simulation.
Support for the gate level. Yeah.
So I can actually run the gate level, and I can make sure that things like the output enable works on the GPIO pads, and yeah, that worked fine.
Awesome. Okay, so any last words from you, Leo?
Hopefully not. Well, I will be at FSIC in July at Frankfurt an der Oder. So if anyone has the opportunity to also be there, I will also talk about Greyhound, make a presentation there, and I would love to actually meet you there. So yeah.
Great. Yeah. So yeah, we've got FSIC coming up in July, and then we've also got ORConf coming up in September. So if you want to meet Leo face to face and say congratulations for such an amazing chip, then make sure you come to one of those conferences. I'm still working on getting you to come to ORConf, but hopefully,
maybe I will.
Great. Okay, well, thanks everyone for tuning in, and maybe we're not going to have a stream next weekend, but next week, but we will the week after. And if you've got anything you want to be covered, then just write in and let me know. So thanks, Leo. Thanks very much for your time. Thanks for joining us, and see you all.
Thank you.
Bye-bye.
Bye.